Welcome again to Julian Stark.
All right, thank you.
I'd like to talk about traffic jams today, because I believe that a lot of companies here too have a traffic jam in their companies. Maybe you won't see it yet, but I hope that by telling our journey from lean to quick response manufacturing, that you guys learn about how you guys create your own traffic jams and actually how you can fix that. So first of all, I'm Julian Stark. I used to work for Kooima Company for the last 3 years. Now I work for POLCA software. Started as an intern. I'll tell a little bit more about that later. This is Kooima Company. Kooima Company is a job shop manufacturer located in Rock Valley, Iowa, northwest Iowa. This is kind of a aerial view of the plant. To get a little bit more specific, first I want to talk about who we are and what we do. Secondly, I would like to tell how we started our project with lean and how we ended up with quick response manufacturing. Thirdly, how we started with implementing physical POLCA tags and actually use POLCA to regulate our working process on the work floor, and what problems we ran into, and how we fixed that with Propulse, the digital version of POLCA. And at the end, I will tell more about the results that we actually got from this project. First of all, Kooima Company, like I said, located in Rock Valley, Iowa. It's a big job shop manufacturer. But actually, we also manufacture parts on inventory. So the first part you see here, is it actually working? Yeah, it is. So this is the turner, the composter. I'll tell a little bit about that later. What we do, we laser cut, bend, and paint, and do a whole bunch of different operations. This is one of our inventory products. It is a header adapter. It goes in between the head of the combine and the combine itself, and it actually transports all the cord and all that into the combine. So we make this entire machine and all the sub parts and everything. We cut it, we bend it, we weld it, we paint it, we do everything. So there's different versions of that header adapter. Another thing we do is we manufacture knives that go into the machines. So it's a spare part replacement, for example, for John Deere or Claas or New Holland, all these type of vehicles. So we make spare parts for that too. A little bit more about the turner. The turner is a composter. You can use it to actually turn around the dirt to make the digestion of the dirt go a little faster. And actually, by doing that, you can save transportation costs, and it makes that process of digestion go a lot faster by composting it every now and then, and that will increase the speed of the process and can save you a lot of transportation costs. So the turner, that's what it does, and as you can see, it has a lot of sub parts. So all these little pieces that actually turn the dirt, and all these pieces and the wheels and everything, it's all separate parts. So imagine how complex that is in a job shop manufacturer to create all these different parts, make them come together at one point, and then weld them, paint them, outsource it, and do all of that stuff, and actually get this done on time at the date that the customer is asking for. So what I told so far, that is about the stock inventory items that we make, but we also make just anything. We are a job shop manufacturer. We can do laser cutting, bending, machining, welding, and a whole lot more. I will tell about that later. But these are kind of the parts that we could manufacture. This is kind of what it looks like. As you can see, tubes, flat material with a whole bunch of bends in it, or flat. It doesn't matter. We can do it all. To tell you a little bit about the process. So first, we basically have two starts in the process. We have the laser cutters and the tube cutters. We have about 20 laser cutting machines for flat material, and about per dozen tube lasers. After that, it goes to the bending operation. For example, flat bending, we have a whole bunch of press brakes that the parts flow into the press brake area and we start bending them, and then sometimes you go to machining or grinding or assembly or welding, and then at the end to shipping. But there's also a whole bunch of other smaller operations that we do, like reaming, the knife cell that we create the knives. We have a water jet, a 3D laser, a lathe, and a whole lot more. So we do a whole bunch of different operations to actually serve our customers the right way. What I'm talking about today will be mostly this area, the laser flats to bend flat area. So I will show you a short video of what that process looks like. So sit back and relax. So to give a little explanation before you guys see the video, what we do is we have a river system or an ASRS system where we load the raw material. So the sheet material is being loaded into that river system. That river system automatically feeds the material into the laser cutters, and then the laser cutters, when they're done, they call an AGV, an automated guided vehicle, one of them automated carts. They drop the cut sheets on the carts, and then it goes to skeleton removal, take the parts out, and then we go to the next operation. So that process you will see in this video. So here you can see the laser cutters. This is where all the raw material is being stored. So here it feeds it into the machines automatically. You know that laser cutters, they start cutting. So the nesters, they nest the parts, send it to the machine. Our system knows exactly what machine needs to go to, feeds it into the laser, start cutting. So next part, when the machine is done, the AGV comes and runs, stops underneath the machine. We drop all the parts, the cut parts in the machine. Drop it on the HV. From there, it goes to skeleton removal, and then to bending, machining, and maybe welding, assembly, shipping, no matter what. It brings you to the next operation. So that's kind of what the process looks like to give you guys an idea. When I first started the internship 3 years ago, I had two goals. One goal was to reduce the lead times. And another goal was to increase the on-time delivery. The management of the company, they wanted to get advice about how they could actually get to this point. And to be a little bit more specific, we wanted to reduce the lead times by at least 30% and to increase the on-time delivery by at least 10%. So that was my goal. That's what I was working toward to. So after school, I actually studied in Rotterdam, the Rotterdam University of Applied Sciences, Industrial Engineering. In school, they taught me this much about lean and this much about quick response manufacturing. So I followed the big crowd, right? I got my lean belts and I was like, let's do this, guys. We're going to start lean, we're going to implement lean, and we can do this and we can actually get to these goals. So we started implementing lean. So just to give you guys a little bit of a idea here, this is our tube laser area, and we started doing 5S and SMED, and this is before. You can see a whole bunch of parts laying here, a whole bunch of junk just everywhere. And after doing our 5S project, it looked clean, it looked pretty nice, and we had some more space. But when we actually started to measure all the lead times again, it didn't really improve. So we were not very happy with it. So actually, I also had a hard time figuring out how can we manage that big of a variety of parts in an environment where lean is about flow or one-piece flow. We don't do that. It is a different type of environment. So I started looking into it a little bit more, and I went to the quick response manufacturing sessions here in Madison. That's where I met Rajan Suri. And he taught me a little bit more about this theory, and I thought that is what we need. So we kind of shift directions, and I kind of wanted to implement quick response manufacturing. So that we went that route, and then actually I started thinking about it. So everybody is thriving or going for operational excellence. And operational excellence, just really easily said, is just being the best, win your from the competition, have a big competitive advantage. That's what operationally excellent means. So we're all striving for that. So in my journey from lean to quick response manufacturing, I kind of started zooming out and kind of looked at all the different tools that we have. And actually how I kind of see it is that there are different toolboxes to get to that point where you can call yourself operationally excellent. So for example, we have Lean Six Sigma. And we have quick response manufacturing, and we have theory of constraints, agile, and all these good tools. They're all very good tools, but I see them as toolboxes with tools in them. So if we open up the toolbox and we look inside these toolboxes, then we can see that there are different tools in there for different purposes. So if we compare these theories with each other, then every tool is made for a different environment. So for example, lean, we all know it. Lean is for the car industry, where you have a mass customization flow. Look at GMC, they make a whole bunch of different cars on the same line, but they're all cars. And there's like a heartbeat in that process, and that's where you can use lean. Or we have Six Sigma. For example, the beer factory, right? We all like that, so I thought it would be a good example. So there's a whole bunch of pipes, and actually all these pipes are connected to each other, and at the end there's a certain type of beer coming out. And if you think about it, it's pretty crazy that that beer in Holland, for example Heineken beer tastes the same here, and it also tastes the same in Holland, but they're made in different plants. How do they do that? They use Six Sigma for that. And then we have quick response manufacturing made for an environment where we have a high mix and low volume environment. For example, Bosch hinges, like we heard earlier this week. So they all have a different focus also. Lean is focusing on waste reduction, taking out all the waste and become more efficient that way. Six Sigma is focusing on no variety, so 100% quality and no variety. And if you think about it, with Lean Six Sigma, they can actually make that work in beer or milk manufacturers. And quick response manufacturing, as we all know, is focusing on lead time reduction. So if we open up the toolbox a little bit more, and we look at the tools that are inside, then we see that every toolbox has its different tools. And what I learned is that all these tools actually can be used in different environments. So it doesn't mean that if I choose for quick response manufacturing that I cannot use 5S or SMED. These are awesome tools, but you have to know in what your environment you're in and what tools to know when, what tools to use at what moment. So that was my first lesson that I learned. Know what environment you're in order to, before diving into the details. So we decided to go for the quick response manufacturing route. We actually started to look at some of our processes, and what I found is that we have a lot of waiting time. Actually, our touch time, and we proved it in our company, is often less than 10%. We found jobs that take 5 weeks to make, and there's only 11 hours of manufacturing times in that job. If you think about it, if I would be this job, I would be so bored. People I'm sitting here waiting, people take me up and start adding value to me, and then I have to sit somewhere else and wait again for a long time, let alone the customer. He is waiting all the time. Like, this is crazy. 10% of the entire lead time is touch time. That is insane. So we agreed that we shouldn't focus on the black space, but first focus on the white space. So that's what we did. So this is actually one of our MCTs that we created. This is one of our parts. Yeah, we kind of know how it works, right? Gray space, white space. And as you can see, it's pretty long. We had a 60-day lead time and a lot of white space. So we started making all these MCTs, and we learned from it. And that was kind of the start of our process. So then when you think about it, how come all this white space? And I would like to compare that to an interstate or a highway. I'm a visual thinker, so that's why. If you think about, like, if you go to Chicago, and just to ask you guys a question, what happens if we utilize the asphalt of the interstate at 100%? What happens? Traffic jam. In a traffic jam, your speed goes down, and sometimes you're even standing still. It's annoying, right? And also, if I would stand right next to the interstate and actually count the amount of cars, if I would draw a line on the interstate and count the amount of cars that come over that line, I would see that if I utilize the asphalt at 100%, that there's less cars coming over that line than when I utilize less of that interstate. So that was one of the biggest lessons we learned. And then I read the book of Rajan Suri, and he actually, that was in line with what he said also. So if you think about your manufacturing process, this is what happens, only then we'll have floating bottlenecks. One time bending is really busy, so there's a traffic jam in front of bending. Another time, machining is really busy, so there's a traffic jam in front of machining area. But also in the office, engineering, think about engineering. There's a stack of papers they have to work through, and that bottom paper is the most important, but they're all just white paper, so who knows that? You know, so that is all indications and signs that you guys might have a traffic jam also. If you see that in your company, you might have a traffic jam. So in comparison to what Rajan taught us, we can see, also compared to the interstate, the more cars there are on the interstate, the longer my travel time will be. And on the other hand, the more cars on the road, the more unpredictable my arrival time will be. And now Rajan proved in his studies that about 80% capacity utilization, that's the point where your speed versus your output is optimal. So in order to create a good relation, or how to say that, like in order to have a good flow, you should schedule your machines at 80%. Compared to the highway, you use less of the asphalt, but actually the flow will go up and the output will go up. So that's our second lesson that we learned. Excess work in process leads to exploding lead times. With other words, if I go over the 80%, my lead times explode. And in order to keep your lead times short, schedule at 80%. So now when we see the connection between amount of cars on the road and lead time, we need a tool to actually start working on that work in process, because it is about work in process. So in order to keep my work in process down, we started using Polka. So imagine we have 4 workstations, A, B, C, and D. And we have 2 orders. Order 1 goes from A to B to D, and order 2 goes from A to C to D. Somebody in the bending cell B, he called in sick and he's not coming, and accidentally there was another machine that broke down, so we have not enough capacity. So cell B, they ran out of capacity and there's a bottleneck. In this case, we think at Kooima it is better to not provide B with any more work, because then we create our own traffic jam. But if in the future, when you're really good at cross-training, this should be an indication that we need extra work at B, that we need extra capacity at cell B. So we are starting to cross-train our people in to actually be able to manage these type of situations. So to explain a little bit more about Polka, I'd like to explain it by using a bar, for example. If you have a bar, and due to laws and regulations, within that bar there can only be 50 people at the same time. Sometimes you see that there's a guard standing in front of the door, and he has 50 poker chips in his hand. Every person who comes in will get 1 poker chip. And then at the end, when they are all drunk, right, and they leave the bar again, they have to give that poker chip back to the guard. And that poker chip that comes back to the guard is an indication for that guard to let more people in. So he can only allow 50 people in that bar. Every person has 1 chip. And when he runs out of poker chips, he cannot allow more people in that bar. So that is kind of what Polka actually is about. Only then, a little bit more complicated. So we connect different loops to each other, and instead of a poker chip, we have this Polka card. We have different cells, cards that flow between cell A and B, and for example, B and E, and every loop is identified with a different card. So for example, if there's a job going from A to B to E, A needs to look at, is this job ready to start? Okay, yes. Second question is, do we have the card for the AB loop? Yep, we have it. So then we put the card, the tag, on the job, and it flows through to cell B. In cell B, they will see the part coming in, and then they know that it has to go to E. So first question is the parts there? Yep, it's right there. Second question is, does cell E have capacity available? With other words, does the guard have that poker chip? Yes, so I get the poker chip, I get the BE tag, and I can move on to the next station. That is how Polka works, just in a nutshell. So this is our process again, and in order to get this 80% capacity deal going, we decided to start a project in the laser flat bend flat area. Just to give you an idea, with 20 lasers, we can cut 2,000 hours a week, and we can drown the people that are in bending flat. We can drown them with work. Like they will drown in work if we aren't careful. So we use Polka to actually regulate the amount of work in process in that cell to create an optimal flow in the bending flat area. So that's what we did. We created a Polka loop between these two cells, printed a whole bunch of tags, and we started putting all the tags on the jobs. But just to give you an idea, we complete a couple hundred jobs a day in that bending cell. So imagine you need 200 tags to take care of. Every tag, we need to grab it when we're done. We walk back to the beginning of the process, put the card back in the slot. So all these cards need to be managed. Cards get smeared. We lose tags, and actually also we have small jobs and big jobs. And on every job we got one card. But what does one card mean? That's what we started to ask ourselves. So one card, is it 1 hour? Is it 10 hours? What does it mean? Because we have 80-hour jobs and we have 20-hour jobs, and both get one tag. So we ran into that problem, and we decided that we needed to find something else. So during my internship and after my internship, I went back to Holland and I actually met Robert Peters from Propos, and we had a fun discussion about Polka and all that, and he created a digital version of Polka, and that to me sounded like exactly what we needed for. How awesome is that? To have a system where we don't have to actually take care of the cards, but the cards actually take care of the process. That is exactly what we need. So to give you an idea, this is in the tube bending area, so later on we expanded Polka to a few other areas. This is what the Polka tags look like on the jobs. But we decided to stop it because it was not manageable, especially if we wanted to add more cells. That was so much work to keep that up and running. So we decided to ask Propos to come in. Propos is a system where it is an add-on to your ERP system. Basically, at Kooima Company, we use Epicor. It is connected to Epicor, and will show the people in the workstations what to work on. Now I'll explain that a little bit farther. So this is kind of what it looks like. Every workstation will get its own screen, and on these screens, they can see exactly what they have to do. So to give you kind of a general idea of how it works, we have the ERP system. In our case, we used Epicor. People put the orders into Epicor, so we create a demand. After a while, MRP runs and we create jobs. Epicor creates jobs. That's where Propos comes in. The jobs are being exported to Propos, and Propos starts back scheduling all these jobs. Based on the routing, every step in the routing will have its own screen, and I will show that later. So after Kooima started scheduling, after Propos started scheduling, the system will send the jobs to the screens out on the floor. And then the people on the floor will interact with the screens. They will touch the jobs started and actually completed. And based on that information, Propulse knows the live environment out on the floor, which is kind of comparable to like a Google Maps or a Waze. I don't know if you're familiar with that app, but if I use Google Maps, I go from city A to city D, so I pass a couple of cities, and I can see beforehand if there's a traffic jam coming up. So that's what Propulse does also. By looking at the entire facility, it looks at where are the bottlenecks, where are the traffic jams, and how can we actually manage that, and it will help the people out on the floor to create triggers on how to prevent that traffic jam from happening before it actually occurs. So after a while, it is possible, like to every couple of minutes, it's possible to get that data back into Epicor or your ERP system, to have that all in line, so that if a job is started in Propulse, you can also see that in your ERP system. So this is kind of what it looks like. Again, this is our process. So we put a screen with every operation that we have, and all these screens, they will show what the people have to work on, and in what order Propulse advises in what order to work on the jobs. So this is really comparable to the departure screen in, for example, Chicago. Everybody can take an airplane nowadays. If you want to go from Chicago to another city, then you just walk up to the screen, and if your flight is on top of the list, you know you have to run. You cannot sit in the lounge anymore. You cannot drink coffee anymore. You have to run. But if your flight is at the bottom of the screen, you know you can relax, take a coffee and a couple of other drinks, and just kind of relax. So that is also how Propulse works. We use the departure screens as an example on how to design Propulse. But also sometimes, this is actually a European example. So Glasgow, which is in Scotland, sometimes it's kind of cloudy there. So it happens that you can actually depart from the city you're in, but you cannot land in the city. You cannot land in Glasgow. So then the flight will be on hold. Other flights will pass the Glasgow flight, and as soon as as soon as the mist is gone, or the clouds are gone, then the on hold sign will disappear, and the flight will flow together with all the other flights, and it will depart later, and you can just take your flight then. So that system is also available in Propulse to have jobs on hold, other jobs flow through, and it keeps managing the jobs for the people out on the work floor, and it makes it really easy for them to see what jobs they should be working on. So I'll explain the screens a little bit. We have two sections: the information screen and the work screen. The work screen consists of three parts. The first part is expected, which, let me explain it like this. Every operation, if I'm working on a job, other parts flow into that operation. When I'm done, I bring my part to the next operation, and walk to the buffer and look at all the jobs that are there, and I grab the next one and start working on it. So this expected screen shows what is coming toward my workstation. When they are done with it, they place the jobs in the buffer, which is the middle section. So that buffer represents all the jobs that are actually in the buffer. When I'm done working on the job that I was working on, I bring it to the next station, walk to the Propulse screen, look at the in buffer section, and I know that the top job is always the most important based on customer demand and the things that are going on the floor. So I walk to the job, I start the top job, I hit it, and then it asks me, do you want to start it? So then it jumps to the next screen in process, then I grab the parts and actually process them. So that's how Propulse works. Customizable information with job numbers, customer names, material thickness, it's customizable. It shows what cell it is currently in, and for the jobs that are in process or in the buffer, it shows what cell to go to next. You can show what machines you run it on and how many hours are expected to work on that job. The due date for the cell, and also all the different notification lines. So kind of like the departure screen, if something is going on that is different than schedule, you will see a notification pop up. For example, we're boarding now, or that plane was just departed. So that type of information is also visible in ProPOS. It will show you when you have a back order, when an order is past due, or when a job is past due. It will show you when you're still waiting for subparts. For example, this one, if you're in welding area, if you click on it, you can see, okay, this part needs to be welded with 4 parts. Part 2 and 3 are here, but 1 and 4 are still in cell X. So you can see that by clicking on it. Material shortage, and for example, the on hold, that is also possible to freeze jobs and quick make changes to it. So, but this is what ProPOS is, but there's also an additional module called Polka. So that's what we implemented at Kooima Company. ProPOS connects all the screens, and these screens are the operations, and between these screens we can make Polka loops. You can decide where to make Polka loops and how to roll it out to your company. But this is kind of what it looks like. So these are so for example, from blue to orange, we know that orange is out of capacity. They're really busy right now, so the cars are empty. The cars are gone. We cannot start any jobs because we can see that the traffic light is on. These jobs are blocked, and all the jobs that go to the orange cell we cannot start. So that is kind of how Polka works in ProPOS. And we can adjust the amount of cards, and right now we totally got rid of the physical cards, and ProPOS is taking care of that entire Polka process between even more cells than what we started with. Right now we use Polka in all the cells at Kooima Company. It totally regulates our working process, and I will tell you about the results later. It is also possible to zoom into a job, so if I click on a job and I want to see a little bit more, you can zoom into it. You can see the print, a 2D picture, maybe a picture of the tub that you have to put the parts in, or a video. If you click on the video, you can see how to set up your machine, for example. Based on your attachments in your ERP system, you can make that show up on ProPOS also. And just kind of other information like inventory, you can kind of dive into the job. So by having all these people touch the screens and actually start and stop jobs, ProPOS is gathering a whole bunch of information. That information can be used for the improvement teams to actually decide where to start a new improvement project. So for example, we can show how the working process actually changed over time between 2 cells. So you can actually dive into that and see, hey, there was a lot of working process in that cell, but by default, there's at least 300 hours laying in that work cell, and that is just sitting there. So then you know that you can actually lower your WIP by 300%, by 300 hours, and actually create more flow that way. Because like for example, if this line does not go underneath that certain line, that means that this amount of WIP is always sitting there. I can take that amount of WIP out, theoretically. By taking that out, you have less WIP on the work floor, resulting in a better flow. So that's how we now use ProPOS in order to improve our processes. But also stuff like on-time delivery for a cell, on-time delivery for the total company, all that information is all in there. And of course, the MCTs. So finally, the results. We went live in November of 2018, so we're just live about half a year. And when this presentation was due, that was in March, I believe, March. Already then we saw good results, and even farther down the line, right now, we see even better results. So to kind of give you an idea, first of all, ProPOS created ease of work on the work floor. Because before, I don't know if you guys are familiar with Apple Core, but you need to click 30 times in order to sign up a job. Like, I'm not even kidding. We actually counted the clicks, and it was 27 clicks in order to sign off the job. We save so much time with ProPOS. You could just click on it, start it, and you're done. So it is so much easier. Another thing is there's way less work in process on the floor. Even in front of welding, where all the parts come together, parts flow together way better than before. And it really helped us to like, for example, that big turner that I just showed, that is a huge assembly. I think there's like 150 different subparts flowing in one spot. That was a headache before we had ProPlus. Now it flows in nicely, and it really helped us to manage that. Our lead times are reduced by 40%, which is kind of hard to measure actually, because we have way different lead times for every part. But overall, we see the parts that we measured that the lead times reduced by 40%, and that number is still going up. So that's very positive. And also our on-time delivery in just the first 3 months made a peak, and it increased by 12%. And there's still a lot of room for improvement, and we can even see it go farther up now in the later months. So these are a couple of the results that we had from implementing ProPlus and Polka. The most important thing is that Polka and ProPlus helped us to regulate the work in process and actually create more flow in order to get to these results. And it is a long journey, and I hope you guys learned from our journey. And believe me, it's an awesome journey, and I hope it's not over yet. It will not be over yet anytime soon. So, thank you so much for your attention.